today we have Takeda Yusuke, who is a researcher down just south of Kyoto, working in this joint, really cool building where when you walk in, the receptionist is a robot and gives you all your instructions to sign in, etc., and talks to you as a kind of humanoid robot. And you can also, as you walk to the cafe, there's a robot that you can sit and chat to. And so it's a really cool building, I thought. Anyway, so when I was there recently visiting Yamashita-san, I got a chance to meet with many different researchers at the building. It's a building joint with, as you can see on the slide, Riken, which is one of the top kind of neuroscience-y places to do research. I mean, they do lots of stuff, but they have a particular strength in neuroscience and quantitative approaches to neuroscience, and joint with ATR, the building there, which also invests in different types of research. And so it's a really cool environment, lots of AI work and other sorts of robotic stuff going on, lots of brain imaging and cool stuff like that. And I was really interested in particular the work that Takeda-san is doing. And so he's got some software and had some recent really nice papers in finding spatiotemporal patterns from resting state brain activity. And in the group, we're very interested in trying to quantify dynamics, trying to find patterns in dynamics, working with big neuroimaging data sets. And so this seemed perfectly aligned with a lot of the interests of people around our group. And so I've invited, and he's kindly agreed to present some of his work to us. So looking forward to your talk, and thanks for joining, Takeda-san.
Yeah. Thank you, Ben-san, for the kind introduction and inviting me to this exciting seminar. I'm very happy to show you our recent works. And please feel free to interrupt me if you have any questions. First, let me briefly introduce myself. I was born in Japan, and currently I'm working at Riken AIP and ATR as a researcher. I have been working on unveiling hidden brain activities from EEG, MEG, and fMRI data. Today, I will show you some brain activities unveiled from resting state data. These are today's topics. First, I will introduce the background and the motivation of our studies. Let me start from brain activity during a task. Suppose that this rectangle represents brain activity. Horizontal axis represents time, and vertical axis represents space. When we present stimuli, such as phase stimuli, stereotypical spatiotemporal patterns appear after stimulus onset, which we call stimulus-evoked activity. This is a sample spatiotemporal pattern which appeared after phase stimuli, MEG, and cortical current estimated from MEG. Here, we define spatiotemporal patterns as activities represented by two-dimensional matrices of space and time, like these. Such patterns are formed by propagating activities through anatomical connectivity. When an activity propagates from blue to red regions through yellow region and return to blue regions, this propagating activity forms a spatiotemporal pattern like this. Therefore, by examining the spatiotemporal patterns after the stimulus onset, we have tried to reveal signal flows related to brain functions such as face perception. On the other hand, how about resting state? In the case of resting state, we don't present stimuli. However, it is possible that spatiotemporal patterns appear after the onset of internal events, such as remember the past and imagine the future. Indeed, repetitive spatiotemporal patterns in resting state brain activities have been widely observed in various species and regions, such as mouse visual cortex, rat visual cortex, mouse whole brain, and human temporal cortex. Therefore, revealing spatiotemporal patterns in resting state brain activities may unveil our internal brain activities, such as consciousness. However, there is a big problem. That is, onset of spatiotemporal patterns are unknown. In the case of resting state, we don't have stimulus or response onset, so we don't know when spatiotemporal patterns appear. To solve this problem, we recently proposed a method, spatiotemporal pattern estimation, STEP in short. STEP estimate repetitive spatiotemporal patterns from resting state brain activity data. This rectangle represents resting state data, time and space. In this data, these patterns appear sometimes, but we don't know when they appear. Only from resting state data, STEP estimates these patterns. STEP assumes that resting state data contains several unknown spatiotemporal patterns at unknown onset. In the case of this figure, resting state data contains 3 kinds of patterns, and each pattern appears for several times. This assumption is mathematically formulated as follows. Resting state data Y consists of the convolution of spatiotemporal pattern P and onset time series U. Note that the onset time series U takes binary values 1 or 0. It takes 1 if onset. The purpose of STEP is to estimate spatiotemporal patterns P and their onset U only from resting state data Y. How to estimate P and U? STEP searches for the optimal P and U that minimize the residual error between observed and reconstructed data. STEP solves this optimization problem by the following procedure. First, we initialize onset U by random numbers. Once onset U is obtained, we can estimate spatiotemporal pattern P by the least squares method. Using the estimated pattern P, we update U so that the residual error becomes smaller. Then we return to the estimation of P. By repeating the estimation of P and updating U, we can estimate P and U simultaneously. STEP has 2 hyperparameters, number and length of spatiotemporal patterns. They are determined so that the reproducibility of estimated patterns becomes high. We divide the data into two segments, and from these segments, separately estimate spatiotemporal patterns and evaluate the similarity of the patterns between the segments. The number and length of the spatiotemporal patterns are determined so that this similarity becomes highest. In 2011, Mazied et al. Proposed a simple method to estimate spatiotemporal pattern from resting state fMRIs. In their method, a segment starting a random time point is served as a template, and sliding correlation between the data and the template is calculated. Peaks are detected in the sliding correlation. Then segment as the peaks are averaged to obtain updated template. These steps from B to D are repeated until the template does not change. The difference of step from this method becomes prominent when spatiotemporal patterns are overlapping. Even in that case, step works, but the method does not. I will show you this by a simulation test. In this simulation test, we generated 5 spatiotemporal patterns like this, and generated their onset time series by random numbers. By convolving the patterns and their onset time series, we obtained signal time series. By adding Gaussian white noise to the signal time series, we generated simulated data, this. When we look at this segment, multiple patterns seems to be overlapping, and their shapes are distorted. Indeed, in this period, 1, 2, 3, 4, 5, 6 patterns exist. From this simulated data, we estimated the pattern by step and Mazied et al.'s method. This figure shows the estimation result. These are true patterns, and these are estimated patterns by step and Mazied et al.'s method. Step successfully estimated the pattern, but their method did not. Therefore, step worked well even when spatiotemporal patterns were overlapping, and that is a common case for MEG and EG. Furthermore, we extended step for big data. Now, resting state data are available on the internet, such as Autism Brain Imaging Data Exchange, ABIDE, Human Connectome Project, and UK Biobank. We extended step for such big data, which we call big step, from many subject resting state data, subject 1, 2, and N. Big step estimate spatiotemporal pattern common across the subject, and the corresponding pattern in each subject specific spatiotemporal patterns. We applied big step to over 1,000 subject resting state fMRIs. The data were obtained from ABIDE 1. This data contains 491 subjects with autism spectrum disorder ASD and 550 typically developed subjects. This figure shows the estimated common spatiotemporal patterns across the subject. Two patterns with the length of 8 seconds were estimated. Horizontal axis represents time from 2 to 8 seconds. The vertical axis represents the height from inferior to superior. The patterns transiently exhibit spatial patterns resembling those of well-known resting state networks, such as positive activity of default mode network, negative activity of sensory motor network, and visual network. The existence of the default mode, sensory motor, and visual networks in the pattern suggests that these networks tend to appear in a time-locked way, like this. On the other hand, we also have many subject-specific spatiotemporal patterns for ASD and typically developed subject. Using these patterns, we examine the difference of the pattern between ASD and typically developed subject. This figure shows the differences in pattern 1. At 4 seconds in pattern 1, large differences were observed around right prefrontal cortex and thalamus. On the other hand, at 4 seconds in pattern 1, the default mode network exhibits the large positive activity. These results suggest that the differences are context dependent. That is, the differences in fMRI activities between ASDs and typically developed subjects do not always occur during the resting state, but tend to occur when the default mode network exhibits large positive activities, like this. This is almost a half of my presentation. If you have any questions, please ask me. Okay.
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 We have a proper session right at the end. I have a few, but nothing pressing.
Yeah. So I go to the next section.
Jinglei has a question.
Sorry, yes, I have a question. Very nice work, firstly, but I'm not clear. How did you define this basic patterns? Did you learn from the data, or it's some predefined patterns? What I mean is that well, we see very regular patterns like an error in the spatial domain, right? How do you define them?
This one?
No, actually, if you go to next slide, we look at the fMRI data.
fMRI.
Maybe let's start. Let me start with another question. So what is the spatial dimension? How big is the spatial dimension? Are they at the voxel level or network level?
That depends on the data. In the case of fMRI, the spatial dimensions are very huge, many 10 million, 10,000 or something. In the case of MEG or EG, the spatial dimension was 63 or 40 or 400. The spatial dimension is depend depends on the data.
Mm-hmm. Yeah, then the next question is about the spatial and the temporal patterns.
Yes.
Do you just select them by the sliding windows on the data, or they are learned as a dictionary or components from the data?
You mentioned about this. No, in our method, we don't calculate sliding window. We just estimate pattern P by optimizing this optimization problem. So
okay, I kind of understand. Okay, it's learned from the data.
yes.
Automatically. Yeah. Well, I previously worked on a method for fMRI analysis, which is called dictionary learning and sparse coding during my PhD. But at that time, I didn't consider the time windows. I just regard each time point as a sample. So I can learn a dictionary of all the fMRI activities across all the subjects. I think the idea is quite similar, but in your work, you included the temporal dimension. Yeah, that's very, very good. Yeah. Thank you. Yeah.
Thanks, Jinglei. Okay. Any other questions? All right. Carry on. Okay, so.
Yes. Yes, then I go to the next section. We applied our proposed methods to resting state MEG and EG data. The MEG and EG data were simultaneously recorded from 12 subjects during a resting state task. In offline analysis, we applied a low-pass filter at 50 Hz and a high-pass filter at 0.4 Hz. Cortical current were estimated by linearly constrained minimum variance beamformer. For each vertex, the current was normalized to have mean 0 and the standard deviation 1. Then, for each subject, we estimated the spatiotemporal patterns from the cortical current. This movie shows a sample pattern. Absolute value of pattern 1 of a subject is shown. The length of the pattern was 0.1 second. Within 0.1 second, the activity globally and consecutively changed with time. This figure shows power distribution of the patterns. The powers were averaged across time and subjects. The pattern had large activities around the cingulate cortex, and here, and here. The activities of these areas, cingulate cortex, were reported to reduce during unconsciousness. There, and this area. So the pattern may reflect consciousness. On the other hand, a previous human ECG study reported spatiotemporal patterns containing oscillatory component around 15 Hz. So we asked whether the pattern estimated from our data also contained similar oscillatory component. To answer this question, we decompose the patterns in each frequency component from delta, theta, gamma, and calculated their powers. This is the procedure to decompose the patterns. Originally, the cortical current had frequency component from 0.4 to 50 Hz. From the current, we estimated the spatiotemporal pattern and their onset. Here, we applied the same onset to narrowly filtered current, such as 8 to 12 Hz, and estimated the pattern at the band. This is repeated for each frequency band. This figure shows the power for each band, delta, theta, alpha, beta, gamma. For all the band, the powers, this blue line, were significantly larger than the surrogate ones, this red line, which were obtained by randomized onset. This result indicates that the pattern consisted of multiple frequency components. This movie shows the sample pattern in each frequency band, delta, theta, alpha, beta, and gamma. Interestingly, the delta activity and gamma activity seem to propagate opposite directions. The delta activity seems to propagate from anterior to posterior. Like this. While the gamma band activity propagates from posterior to anterior. But anyway, the existence of these activities in a pattern indicates that they occurred in a time-locked way. By the way, resting state networks are very popular in resting state studies. So next, we characterize the pattern by resting state networks. We downloaded the spatial pattern of resting state network of fMRIs from BrainMap ICA, these 9 spatial patterns. And for each time in each pattern, we evaluated its similarity with the resting state network by correlation coefficient. And this was repeated by changing time. And this figure shows the frequency of high correlation coefficient. Horizontal axis represent the frequency band, delta and gamma. And vertical axis represent resting state network of fMRI, visual 1, visual 2. This result indicates that the beta band component in the patterns frequently exhibit the spatial patterns resembling those of sensory motor networks. And alpha band component exhibit the default mode network. Anyway, the patterns exhibit the frequency-specific resting state networks. Our simulation experiment using chromato oscillators suggests that the patterns reflected propagating activities in metastable brain states. Metastability is a dynamical phenomenon in which the system's state spontaneously cycles between multiple weakly attracting states. Our results suggest that the patterns reflected the fixed past that the state repeatedly went through in the metastable brain dynamics, like this. Let me discuss the result. The patterns consisted of the multiple frequency component, each of which exhibited the frequency-specific resting state network of fMRIs. This result suggests that the patterns reflected a process to integrate the information distributed over the frequencies and networks. I showed that the patterns contains the beta band component and beta band component resembling the sensory motor networks and alpha band component resembling the default mode network, and so on. The existence of these activities in a pattern indicates that these activities occur in a time-locked way. Therefore, the patterns may reflect the integration of information distributed over these activities. These results and suggestions brought about our current project. I will show you preliminary results. In the previous section, I suggest that the spatiotemporal pattern estimated from the resting state MEG and EG data may reflect a process to integrate the information distributed over the frequency and networks. If so, how and which information is integrated? To answer this question, we reveal signal flows and their roles in the spatiotemporal patterns. Here, we want to estimate these arrows and which information these arrows reflect, visual or sensory motor. To reveal these, we use the Cambridge Center for Aging Neuroscience dataset, which contains over 600 subject resting state data and their behavioral data, such as visual short-term memory. For each subject, we estimated the spatiotemporal patterns in the same way as our previous study. This movie shows a sample pattern. Within 0.1 second, the activities globally and consecutively changed with time. As in our previous study, the pattern had large activities around cingulate cortex, here and here. And as I mentioned before, the activities of these areas, cingulate cortex, were reported to reduce during unconsciousness. Therefore, these patterns may also reflect consciousness. Then, to reveal signal flows in a pattern, we represent the pattern by state transitions. State transition. As in our previous study, we decompose the pattern into each frequency component and evaluated its similarity with resting state networks of fMRI by correlation coefficient. Based on the correlation coefficient, we define a state in each time. This figure shows a correlation coefficient calculated from a pattern. Correlation coefficient for the delta band component for the 9 resting state networks, and so on. And for each time, we detected the highest correlation coefficient and assigned the corresponding activity as state. For example, for the first time point, the delta band activity at the default mode network exhibits the highest correlation coefficient. So this activity was assigned as a state for this time point. This is repeated for all the patterns of all the subjects. From the state transition of all the subjects, all the patterns, we calculated the the probability of state transitions. This figure shows the resultant probability. State transitions between the beta and gamma band activity frequently occurred as a sensory motor network. State transitions between the alpha band activity as the default mode network and beta band activity as the sensory motor network frequently occurred. This is a schematic illustration of the state transition probabilities. The width of the arrow represents the state transition probability. The beta band activity at the sensory motor network seems to be a half state. Then we examined the relationship between the state transition probabilities and behavioral scores. This figure shows the correlation coefficient between the state transition probabilities and the capacity of visual short-term memory. The probability of state transition from beta to alpha band activities as the visual network was significantly correlated with the capacity of the visual short-term memory. This figure shows a correlation with IQ scores. The probability of the state transitions from beta to alpha band activities as the default mode network was significantly correlated with the IQ scores. This is a schematic illustration of the state transitions and the correlations. The state transition probabilities from beta to alpha band as a visual network was correlated with the capacity of visual short-term memory. The state transition probabilities from beta to alpha band as a default mode network was correlated with the IQ scores. This result suggests that the beta band activity as sensory motor network is a half state, and some of the signal flows in the patterns may reflect visual memory and intelligence. And finally, let me introduce our software used in our studies. We have developed and used these two MATLAB toolboxes: Variational Bayesian Multimodal Encephalography, VBMG in short, and Big Step. Using VBMG, we can estimate and visualize cortical activity from MG and EG data. Recently, my colleague made a nice movie introducing VBMG, so let me show you. And using the Big Step toolbox, you can estimate spatiotemporal pattern from resting state data. And this toolbox includes the functions of step and pick steps. You can download it from GitHub. So please use this software. These works are collaborative research with these members, Riken and ATR and Showa University. I would like to thank all the collaborators. This is the end of my presentation. Thank you for your attention.